Linear Control Systems, lecture number 25. I'm your instructor Yasir Amir Khan, and in this lecture we will discuss gain margin and phase margin. It's a very important concept related to the Nyquist topic that we have been discussing in the past few lectures. So let's start with today's lecture. First of all, this is page number 574 of your textbook and article number 10.6, gain margin and phase margin by Nyquist diagram. With all the previous discussions and lectures, we are able to sketch, interpret Nyquist diagram and determine closed loop system stability. So far what we have studied is that we are able to make the Nyquist diagram, and from the Nyquist diagram we can determine whether the system is stable or not, and that's a very good tool that we have now. In addition to root locus, route Hurwitz, this Nyquist method is a very useful and important tool, and of course in addition to Bode plot. So Bode is a frequency domain method, Nyquist is also a frequency domain method. Now using Nyquist diagram, we will define two quantities. As measures of how much stable a system is. So far in our Nyquist method, we have considered and seen that how we can find out that the given closed loop system is stable or unstable. And now we will talk about how much it is stable. If it is stable, how much it is stable. We will quantify this stability, that how much it is stable, that to what extent we can put burden on the system and it will not fail, it will not become unstable. So therefore, the quantities that we will define in today's lecture are gain margin and phase margin. We will define and we will understand these two quantities, which are gain margin and phase margin. Now, one thing that we should remember and note is that system with larger gain margin and phase margin can withstand greater changes in system parameters before becoming unstable. Gain margin and phase margin are two quantities that we are going to define just next. And a system which has greater gain margin, greater phase margin, that system will not become unstable very easily, very quickly with small change in the system parameters. So it's going to be a robust system. The robustness of the system depends on this gain margin and phase margin. A system having a large gain margin and a phase margin will be more robust, and it will be less prone to the changes in instability resulting in the changes in the system parameters. For example, let me give you an example. There's a automotive braking system that is used nowadays in modern vehicles, and in that system the brake button is not directly or hydraulically connected with the brakes. Instead there's a network in between it, and just like we have the Ethernet in our domestic and in stationary applications, in car there's a CAN bus. So what happens is that if there's a packet loss, but still the system is able to the car gets the brakes, and you can stop the car if there are packet losses as well. Now, how much packet losses can be tolerated? Because each time you get a packet loss, there's a delay in the signal reaching the actuator. So how much delay can be tolerated by the system? The concept of gain margin is directly involved over here. That we design the system in such a way that it has a large the concept of gain margin and phase margin is directly involved here. We design the system in such a way that the system has a large phase margin. It's able to withstand a lot of packet losses and still functions, and system does not become unstable and break does not fail. So these concepts are very important and have a lot of application in the real world systems. Now the concept of gain margin is qualitatively related to the root locus. If you recall, in root locus, we already know that the closed loop poles that are very far away towards left hand side from the j omega axis are said to be more stable, and those which have the poles that are closer to the imaginary axis, and then when the poles are on the imaginary axis, system becomes marginally stable, and then when they move to the right hand side, the system becomes unstable. So similarly, in gain margin and phase margin, systems having larger gain margin and for larger phase margin are said to be more stable. So here we have the definition of gain margin. Okay, first of all, let us define gain margin. Gain margin is defined as gain margin is the change in the open loop gain expressed in decibels required at 180 degrees of phase shift to make the closed loop system unstable. This is the formal definition of gain margin, which you should remember and learn. Basically, by gain margin we mean that how much margin is there in the gain, how much increase in the gain is possible under the worst case scenario, that is with the phase shift of 180 degrees, that is allowed. That is if you increase the gain above that amount, then the system will become unstable. Before making the system unstable, how much margin is there, how much increase in the gain is allowed, is possible, you can do it without making the system unstable. So that is the concept of gain margin, and we express it in decibels, 20 log of that amount. So basically, as you will see in the figure in the upcoming slide, in the Nyquist diagram, the point where the Nyquist diagram cuts the real axis, where the angle is 180 degrees, let us say that point is for example A minus A with an angle of 180 degrees. Then the reciprocal of that A will give you the gain margin, because if you increase that gain at that point, that is A, by this much amount, then the Nyquist diagram will cut the critical point, that is -1. Right now you may not be understanding this thing, but don't worry about it. In the upcoming slide we will consider it, and I will explain with the help of a diagram, so don't worry about it. So let's read this gain margin definition again. At the moment we are introducing the definition of gain margin. Gain margin is the change in the open loop gain expressed in decibels, dBs, required at 180 degree of phase shift to make the closed loop system unstable. That is the definition of gain margin. Now let's see what is meant by phase margin. So here we have the definition of phase margin. Phase margin is the change in the open loop phase shift required at unity gain to make the closed loop system unstable. Phase margin is the change in the open loop phase margin is the change in the open loop phase shift required at unity gain to make the closed loop system unstable. Basically, by this phase margin we mean that under the worst case scenario, the amount of phase shift that you can induce in the signal, that is allowed, that is permissible, that is the margin of the phase shift that you can do in it, and if you increase any phase shift above that amount, then the system will become unstable. This These two concepts are very important. They have a lot of applications. For example, in the modern cars which do not have the brake pedal and hydraulic system, they have electronic system. The brake pedal is not directly connected to the brakes. What is actually happening is that brake is just a switch. It generates a signal and then it is connected through through a network. Just like we have Ethernet, there is CAN bus. The network is used in automobiles. The signal is sent through that network to the actuator, and during which packet losses also occur. Now, each time a packet loss occurs, there is a phase delay in the there is a time delay, phase shift in the signal. The system is designed in such a way that it's able to allow a certain amount of time delay or a phase shift. It has certain amount of phase margin, and that is calculated beforehand. That is designed and kept in the system as a design parameter, so that if the packet losses take place under the worst case scenario, still the brake system of the car functions. You can do a bit of study about this. I encourage you, and I will urge you that you should do a bit of study about this concept of phase margin and the modern electronic wireless braking system used in automobiles. Now let us try to understand both concepts of phase margin and gain margin through the diagram. This is figure 10.35, which shows the Nyquist diagram, and we can see that the gain margin and the phase margin are elaborated in this diagram. Now this is a Nyquist diagram of some system, and it's plotted on a GH plane. Vertical axis is the imaginary axis and horizontal axis is the real axis, and we can see that there's a Nyquist diagram. The Nyquist diagram cuts the real axis at a point that is minus 1 upon a. Let us say that the point is minus 1 upon a. After that it goes to the origin. Now the other thing that we have done over here is we have drawn a circle of radius equal to 1. That is called a unit circle. We have drawn a unit circle with the origin of this with the center of the circle at the origin of the graph, and this circle has a radius of 1. Now there are one thing that you can see, that the distance from the point where the Nyquist diagram cuts the real axis, that is minus 1 upon a, up to the critical point, that is minus 1, is called the this is the gain difference between instability. As you can see over here, here, this is the point number 1, and you can see that there the distance is marked from the Nyquist diagram where it cuts the real axis up to the critical point of minus 1. This is called the gain difference, and you can see that the point where the Nyquist diagram cuts the real axis, we have marked it by minus 1 upon a. Let us say it has any value and we are calling it minus 1 upon a. Now when this is the situation, then we say the gain margin is 20 log of a. The gain margin is, you can see over here, is 20 log of a, where a comes from over here. That is minus 1 upon a. We take this as, we take its reciprocal and multiply it by 1, minus 1, and then we take its log and multiply with 20. That gives us the gain margin. So gain margin is 20 log of a. And now come to the phase margin. Now before moving to the phase margin, try to understand it. What is meant by gain margin? Gain margin is basically it's the margin in the gain that we have before making the system unstable. Now if we increase the gain by an amount of A, then what will happen is that the Nyquist diagram, which is passing from this point, it will pass from this point like this. If like I have said in the previous lecture, that when we multiply the Nyquist, when we multiply the loop gain by some gain, then there is an expansion in the Nyquist diagram. If you multiply it by A, suppose, then Nyquist diagram will expand. And as you can see over here, as I have drawn this orange line, this Nyquist diagram will expand, and previously it was passing from the point -1 upon A. Now after multiplying it by A, it passes from the point -1. -1 point is the critical point. It's also called the critical point. And when this happens, the system becomes marginally stable. Before that, if the system is stable, then when this happens, the system becomes marginally stable. So we say that there is this much margin in the gain of the system. You can increase it by an amount of A, and the system will become marginally stable. And when we express it in decibels, then it becomes 20 log of A. That is called the gain margin of the system. We express the gain margin in decibels. If you have any kind of confusion, feel free to contact me. Now let's focus on the phase margin over here. Phase margin is basically as written in point number 2 over here. Phase margin is phase difference between instability. All you have to do is that see the point where unit circle cuts the Nyquist diagram, that is this point over here. The Nyquist diagram is cut by the unit circle over here. Now phase margin is the amount of angle, it's the angle by which you can rotate this Nyquist diagram and make the system marginally stable, and afterwards it becomes unstable. This means that if the amount or the margin to which you can rotate the Nyquist diagram in this direction, you can rotate this Nyquist diagram in this direction, and the Nyquist diagram cuts the -1 critical point. Imagine it, we are rotating this Nyquist diagram like this, and when we rotate it, then this point moves over here and it cuts the -1 or critical point. And when this happens, then the system no longer remains stable. It becomes marginally stable, and after that it will become unstable. So the amount of that angle by which we can rotate it without making the system unstable is alpha, as marked over here. This angle alpha gives us the phase margin of the system. Now one thing that you must note is that when we want to calculate the phase margin, then we have to we have this angle. We have this angle, and we know that this angle is 180 degrees or -180 degrees. We subtract this angle from this 180 degrees, then we can get alpha. As you will see in the example that we will solve shortly, we basically will be calculating the phase margin by subtracting two angles. Therefore, before you get confused or you get you're not able to understand it, before that happens, I am explaining this point that phase margin is actually this angle, which you can see over here, the angle from here to here. This angle, this is alpha, as marked over here. It is the angle by which, if you rotate the Nyquist diagram, in this direction, then the point, this point will come over here, minus 1, and the system will become marginally stable. System will not remain stable. So the amount of angle by which you can rotate the Nyquist diagram and the system remains stable, that is called the phase margin, and that amount of angle is this alpha. This is we call alpha. If still you have anything you are not able to understand, anything is not clear, you can call me, ask me, write to me, and make the concepts clear. So phase margin, so let me summarize it again. Phase margin, it's the amount, is the angle by which you can rotate the Nyquist diagram in clockwise direction, and the Nyquist diagram cuts the -1 point, or the amount of angle by which you can rotate the Nyquist diagram without making the system unstable. That is called the phase margin. And it is actually the delay in the phase angle that you can that this can happen in the system, that can happen to the signal as it passes through the loop due to any reason whatsoever. The amount of phase change in phase shift, phase delay, time delay that happens in a signal as it passes through the loop due to any angle which the system can tolerate without becoming unstable. We call that phase margin. That system can handle this much amount of delay or phase shift in the signal, and after that, if more phase shift happens, then the system will become unstable. So that's the concept of phase margin. And then the concept of gain margin is that the amount of gain, that increase in gain that is allowed or possible without making the system unstable. That is called the gain margin. I hope now things are clear, and let's move forward. We have the example over here, example number 10.8. In this example, we are given an open loop function k upon s square plus 2s plus 2s plus 2, and we have to find the phase margin and the gain margin with k is equal to 6. Now, one way of solving this problem is that draw the Nyquist diagram and determine the gain margin and the phase margin graphically from it. That is very simple. What you have to do is that on the graph paper, properly, neatly draw the Nyquist diagram and find out the point where the Nyquist diagram cuts the real axis. This point, that is, determine this point, and this will be any negative number, and then you take the reciprocal of it, multiply it with -1, make it positive, and take reciprocal of this number and multiply it with take its log and multiply with 20 log of, suppose this number happens to be -1 upon a. You use this a, we take 20 log of a, that will give us the gain margin of the system, and that is simply measuring the quantities from the graph. And regarding the phase margin, for phase margin, what you have to do is simply neatly draw the Nyquist diagram. Suppose this is our Nyquist diagram. Draw a unit circle on it. This is suppose our unit circle. It passes for like this. We have, suppose, in this form, and this is our unit circle, roughly drawing it. This point, you measure this angle using a D or a protractor, and you get the phase margin of the system. Measure this angle from here to here. In this way you get the phase margin. That is a graphical method. The mathematical method, the other way, is that we will consider in this example is that, first of all, put s is equal to j omega in the open loop function, and you can see that over here in this right now. This is the open loop function where we have substituted s is equal to j omega. Now after doing this, generate a table. Make a table. As you can see over here, this is our table where we have omega, then we have the mod of the open loop function, then we have the angle of the open loop function, and we substitute different values of omega starting from 0, then we keep on increasing and then keep on increasing. Basically our target, what is our target? Our target is that we have to find two things. First of all, we have to find this. We have to find that frequency where we get an angle of 180 degrees and the corresponding magnitude at some frequency. By this is a sort of trial and error method, a numerical method. You put in different value, you generate a table, and then you try to find out omega where we get an angle of 180 degrees or 180 degrees, 180 degrees or minus 180 degrees, and note this magnitude. This is this minus 0.3, its reciprocal is actually we take the log of the reciprocal, and that is our gain margin. And then the next thing that we do is that we find this frequency. This is that frequency where we get a magnitude of unity. We try to find out a frequency in such a way that we get the magnitude equal to 1, and at that we find the angle. We are looking for this angle. This angle, from this angle we will calculate the phase margin. We for a frequency which is this, you can see over here, and from this frequency, this is that frequency where we have a gain of 1 unity gain, and we note the angle that is occurring at that unity gain, and from there we will calculate the phase margin of the system. So let's see how we calculate those. I have actually done the working. When you will be doing it, you will actually be looking for these frequencies, and you will have to generate a lot of values, and then you will look for this thing where we get an angle of minus 180 degrees. Then you will look for this thing where we get a gain of unity, and for minus 180 degrees you note this magnitude part, and for the unity gain you will note this angle part to find out the phase margin and gain margin. So let me repeat it again. Basically we generate a table. We put different values of omega starting from 0, and then we calculate using this open loop function where we have substituted s is equal to j omega. Using this gives us complex number. It has two parts, the magnitude part and the angle part. Putting different values of omega, we find out the magnitudes and we find out the angles. We do this to find two things. First thing is that we find the gain so that the angle is minus 180 degrees. The second thing that we find is that we find the angle, this angle, so that the gain is unity. We find two things, and these are the corresponding frequencies. We note these frequencies as well. From them we will calculate the phase margin and the gain margin as shown in the next slide over here. First of all, we find the gain margin. For gain margin, as you can see over here, the point where the angle was 180 degrees was 0.3. So we have written it as minus 0.3, that is 0.3 angle 180 degrees. We say that this thing is minus 1 upon A, and from here we get A is equal to 3.33. Then we take the 20 log of A, that is 20 log of 3.33, and we get the gain margin of the system, that is 10.45 decibels. So it's simple mathematical working. We have noted this point where the angle is 180 degrees, and noted this corresponding point, and then that is our minus 1 upon A. From there we calculated the A 0.33, then we took the 20 log of this A and we get our gain margin. That's all we have to do for it, and we get the gain margin that is required, and that happens at this frequency under root 6 radians per second. Now come to the phase margin. For phase margin, we had noted that the angle at which the magnitude mod of g of j omega h of j omega was 1, that angle was minus 112.3 degrees, and that was happening at a frequency of 1.253. We are getting this angle. This angle is actually measured from the x-axis. This is this angle measured from here to here, and we have to find this alpha shown over here. We are interested in this alpha, as you can see over here. Therefore, alpha is simply, we subtract from 180 this 112.3. We get alpha by subtracting 112 from 180, and that gives us the phase margin alpha. This is the phase margin. So we don't directly get the phase margin from here, rather we get it from here. We subtract this from 180 degrees, and we get the phase margin as shown over here. So in this way we calculate the gain margin and the phase margin of any system from the Nyquist diagram. If you have any kind of queries, confusion, questions, feel free to ask me. You can write to me, you can send your voice note, you can call me, and try to work out with this example, and do the book reading as well. These two concepts are very important concepts. Okay, so now we will talk about the relationship between Bode plot and the gain margin, phase margin. We can determine the gain margin and the phase margin from the Bode plot as well. In this slide you can see the Bode plot and magnitude part and the phase part. Details are not given here, but for the sake of understanding of the topic of gain margin and phase margin, we will be focusing on that portion. The top graph shows the magnitude part. On the y-axis we have the magnitude in decibels, and on the x-axis we have the frequency, and it's plotted on the logarithmic scale. So we have a semi-logarithmic graph paper, and we plot the Bode plot on that. In the second figure, the bottom graph, the y-axis has the phase angle in degrees, and on the x-axis we have the frequency, and we again plotted on the semi-logarithmic graph paper. Now what is happening over here is that if we draw the Bode plot of some given system, then one thing that you must remember is that Bode is plotted for the closed loop transfer function g upon 1 plus gh, and the Nyquist is Nyquist plot is made for the open loop function gh, but they both give the same amount of information, that rather I would say about the phase margin and the gain margin, and they give the information about the closed loop system stability, about the closed loop system, that is g upon 1 plus gh. So when you make the comparison, you must be careful. You don't start making the Bode plot for the open loop function. You make the Bode plot for the closed loop transfer function. Now having said that, if you look over here, the lower bottom line, which is the phase plot, it cuts the 180 degree line, we can say minus 180 line, at a frequency that is marked over here as, you can see over here, omega gm. At this frequency, if we draw a line as shown over here, then from here we get the gain margin. the distance from below the x-axis up to this point. This is called the gain margin of the system. This distance is called the gain margin. How we get it? We draw the line from this point where the lower graph phase plot cuts the minus 180 degree line, and from there we draw this line and we note this point over here on the magnitude part of the border plot, and the distance below the x-axis up to this point is called the gain margin of the system. We can get the gain margin from the border plot as well. That's the point. Secondly, the phase margin is obtained where there is the zero crossing of this magnitude part of the border plot, and we draw a line up to the phase plot and we note this point, and this distance from here to the x-axis to the minus 180 degrees line, this is called the phase margin, because we have the y-axis is calibrated in degrees and that is representing the phase angle. This is called the phase margin of the system, and the frequency at which this is occurring is omega phi m. So in this way we can find out the gain margin and the phase margin from the border plot as well. Let me repeat it once again. The top graph shows the magnitude part of the border plot and the lower shows the phase part of the border plot. We have, as you can see over here, we have this line showing the magnitude part of the border plot, and this is showing the corresponds to the phase part of the border plot. Now in this we find out the point where this line of the phase plot cuts the minus 180 degree line, and we draw a line just exactly above it to the point, or to this point on the magnitude part of the border plot. And what we do next is we measure this distance below the x-axis from here to here, this distance, and in decibels, and this gives us the gain margin of the system directly in decibels. Gain margin is in decibels, and we don't need to take the log etc. like we were taking in the Nyquist case. So this gives us the gain margin of the system. Now similarly, what we do is that we find out the point where the graph of magnitude cuts the x-axis, and then we find the point exactly below it, exactly below this. As you can see over here, we identify this point, and then we measure the distance along the y-axis from here to here up to minus 180 degrees. This difference of angle is in degrees because the y-axis is calibrated in degrees. This gives us the phase margin of the system. So we can measure the gain margin, the phase margin from the border plot as well. But one thing that you should remember is that we make the border plot from the closed loop transfer function, whereas when we make the Nyquist, for that we use the open loop function GH. Now this was one thing. Now let's move to the next slide. As you can see over here, this is an example that we will solve over here. In this example, open loop function is given to us, and open loop function gh is 1 upon s plus 10, and we are supposed to find the gain margin and the phase margin. Now one way of solving this problem is to make the Nyquist plot, and from the Nyquist plot we can determine the gain margin and the phase margin. I will assign you this exercise, practice exercise, that you should make a Nyquist plot, and properly select the scale and make the Nyquist plot properly and measure the. Now in this example, the method we have followed is not graphical method. What we have done over here is we have made a table. First of all, we substituted s is equal to j omega in our given open loop function, as you can see over here, and we get this g of j omega, h of j omega, 1 upon j omega plus 10. And then we have generated the table, which you can see over here. In the table, in the first column we have omega, and in the second column we have the open loop function g of j omega, h of j omega, and we start with substituting omega is equal to 0, and then we solve it, put that omega is equal to 0 into this open loop function, and then we solve it and we get this result, 0.1 angle 0 degrees. Then we put omega is equal to 1 radian per second, and we solve it and we get this value. Then we put 10 and we keep on doing it. One thing that becomes clear after putting these values is that the angle is no longer moving above or beyond minus 90 degrees. It is converging to minus 90 degrees. So the angle is not going towards 180 degrees. One thing. The second thing is that nowhere here you can see that the magnitude is starting from 0 up to very large value, that is 1,000,000,000, that is 1 billion. Gain is not becoming 1, and rather it is decreasing. It keeps on decreasing and decreasing and so on. So what is happening over here is that the angle, first of all, is not becoming 180, that we get then we are able to measure the corresponding magnitude from there, and get the gain margin from there by taking the reciprocal and 20 log of that reciprocal. We cannot do it over here in this problem, one thing. And second thing is that we are not getting unity gain, so that if we get unity gain, we measure the angle, and from the angle after subtracting that angle from 180 degrees, we get the phase margin. We are not getting both of the things. Neither we are getting the unity gain over here in the magnitudes, nor we are getting the angle to be 180 degrees, as you can see over here, and it is converging to minus 90 degrees. So this means that when this is the case, this means that the gain margin is infinity and the phase margin is also infinity. That is, we can have any gain in the system, any positive value in the system as gain, and system will remain stable, and we can have any amount of phase delay in the system, and the system will not become unstable. So this system has infinite gain margin and infinite phase margin. Now this thing we have done by making the table. You could have done it by the graphical method, just I have told you earlier. In graphical method, in such cases, when we make a Nyquist, the Nyquist is normally like this, roughly like this. If you rotate this to any angle, if rotate it in clockwise direction to any angle, it will never cut the -1 critical point. So the phase margin is infinity. You keep on rotating it forever and it will never reach this -1 point, one thing. So phase margin is infinity. The second thing is that about the gain margin, the Nyquist would be something like this. This is half of the Nyquist and we have -1 over here. You can see that this distance here to here, this point, we measure the point where the Nyquist cuts the real axis, it's at 0. So when you take the reciprocal of the 0, that is infinity, and when we convert it into decibels, even then it remains infinity. Therefore the gain margin for this kind of Nyquist would be infinity. Now what you have to do is that you have to make a good clean Nyquist plot of this given system and try to find the gain margin and the phase margin graphically from the Nyquist plot. And then of course you have to solve this example, generate this table and get these results of infinite gain and phase margin. This is also part of your exercise. So the time that you are given right now, you should spend that in solving this gain margin, phase margin, and contact me immediately. Call me, send a voice note, send a text message to the group or personally, and you can give the list of queries to your CR and you can have these questions answered. That is basically the point of watching the lecture according to the timetable, and watch the lectures according to the timetable, and according to the timetable I will be available, I remain available to answer all your queries. And you can also send your queries and you can make a list of the questions and send it to your CR and they can then pass it on to me and I can arrange a special video for that as well. So it's your duty to concentrate and give importance to your studies and don't waste your time. So please try to solve all the examples and the concepts that we have covered in today's lecture, and book reading is a must. Remember that. So here we end our today's lecture, and feel free to contact me. And book, don't forget, I am repeating this thing, don't forget that book reading is a must. Thank you.